Hello, space fans. In this video, I wanted to discuss the historical tracking of satellites over time and their orbital elements. This is useful for determining a pattern of life or what is considered normal day to day behavior for a particular satellite. So, obviously, having a history of orbital parameters for each satellite is important, and having ways to quickly and easily visualize these and changes in them is what the Elset History plot allows us to do. So here I'm going to use Space UI again, proceed as guest. This time we're going to go to SC Analysis, which stands for Space Cockpit Analysis. This will load up Space Cockpit on the left, an Elset History plot on the top right, and a light curve plot in the bottom right, but we're not going to use the light curve plot for now, so I'm just going to scroll this away here and get full screen on the orbital element history plot. There we go. So let's start by analyzing a geostationary satellite. So here we're going to choose LuchaLimp 40258. What that's going to do is load up the Elset history plot here on the right, and it'll also load up Space Cockpit with LuchaLimp in it for us. There's Luch. Right, so here in the Elset history plot, we are given a longitude drift, longitude, inclination, RAN, argument of perigee, and then there's this energy tab, which has a number of other plots, which I'll go through in time. But let's start up here and look at the longitude drift in degrees per day. So you can see here it's hovering around 0. There's very small deviation off 0 here. You can also see that in Space Cockpit by toggling on the longitude drift velocity vector here. So at Geo, if you are above Geo, you'll be orbiting slower than everyone else relative to people at Geo. So that will create a westward drift. If you are below Geo, you're closer to the Earth, your velocity will be higher than everyone else at Geo, and that will induce an eastward drift. So if we're stable and we're playing nice at Geo, our drift rate will be around 0 degrees per day. You can see the impact of our change in longitude. There hasn't been really impacting our change in longitude because we don't have much drift. The inclination here is also pretty steady. Note this is just for the last 7 days. For Elset history plots, you'll probably want to go back a bit further in order to get some decent trending on what's going on. At Geo, we do have a tendency for our inclination to drift, as well as our longitude to drift towards one of these points here, 105.3 degrees west or 75.1 degrees. So whichever one of those you're closest to, if left up to its own devices, your inclination will slowly start to increase and oscillate, and eventually it'll get to around 11 degrees, I think, and then it will slowly start to come back down. And you will start to drift in longitude towards one of these low points, whichever one you're closest to. So in this case, it'll probably be 75 degrees east that we would drift towards. Okay, so here over a 30-day period, you can see once again, there is not much in the way of change in longitude. We're only within 1/100th of a degree here change, and our inclination is pretty steady. So let's go back maybe 2 years for LuchaLimp. Now we can see a really marked change in some of these values. So the longitude here back in June, July 2022, we were around 61 degrees east. And now today we've been sitting here at around negative 18 degrees. You can also bring this up in Space Cockpit just by right clicking. You can see here 18 degrees west. It's the same as negative 18 degrees. So back in July, around 16th, 17th, looks like Luch has done a big maneuver here. So we can actually go back and analyze that scenario. If we propagate back in time to July 2022, I think it was around the 17th, I said. Now you can see, yep, we're drifting to the west at 1 degrees west per day. So we're in the middle of that drift now. It's also useful sometimes to lock the coordinate axes here. So here I'm just going to look at the radial in-track component of the orbit, and you can see we're above Geo, so we're traveling slower than everyone else at Geo. So relative to Geo, we're drifting to the west at a bit over a degree per day. And as we move the simulation out, you can see we're just going to continue that drift. So we can replay this whole scenario of what Luch did over this time period. So what he actually did was drift towards another object that we now know about, called Intelsat Sat-37 Echo. You can see he's got quite a long way to go to get there. And it took a number of months to get over there. You see there I just propagated 2 months out. I just jump back a little bit here, about a month. And we can watch the approach. See if I propagate a couple of days at a time. You can see us slowly encroaching on Intelsat 37. And this is what I meant when I was going over the Geo neighborhood plot. At Geo, you got a lot of time to see people coming. You can see here, it's happening over months for a maneuver this large. Got another couple of days. And you can see we've started to lower our apogee now. We're recircularizing our orbit just to the west of Intelsat 37. So he sat about 250 kilometers downrange and then slowly inched his way back towards Intelsat 37. These Elset history plots are very good at flagging historical events and big maneuvers. They're not very good at giving us timely notifications of when a maneuver has just taken place. It often takes a long time for the sensor providers to perform a new IOD and OD after a maneuver has taken place. So these LSETs are a lagging indicator of a maneuver. But for big things like this particular maneuver at Geo, for example, it took months to play out. We can definitely catch them within this sort of arcing over phase. And then we can keep an eye on that satellite while it's doing its drift. And then we start to look for when it starts to recircularize its orbit and get an idea of where it's going to re-enter the belt. So here we can also look at an energy plot. So these are all the energy values, such as the semi-major axis. You can see there a large increase in semi-major axis to put them above Geo, which increased the orbit period. The eccentricity was unaffected. Our mean motion, so the number of revolutions per day, went down because it takes us longer to do a single orbit. So tracking the energy components is a bit more advanced, but it's useful, particularly if we start to look at things in LEO. So here, I'll get rid of this Geo scenario. Let's look at Blue Walker 3, so 53807. Add him to the scene here. So this is a LEO bird, a large phased array, commercial phased array, run by AST Space Mobile. So here, because we're in LEO, our longitude isn't really that relevant. We don't really care about our longitude and longitude drift because it's changing all the time because we're in low Earth orbit. But we are concerned about our inclination and other orbital elements. So here I'll go back 30 days. Actually, let's go back 2 years as well. So we have everything, bring in everything we have. So here we can see the inclination is recently, well not recently, but the last couple of months has really started to increase in an uncontrolled sort of fashion. So that would kind of indicate that Blue Walker 3 is not performing station keeps, because generally you'd want to keep this inclination to a nice tight band. So it looks like orbital perturbations have taken over here and the inclination is starting to climb. The RAN and argument of perigee, these are going to switch between 0 and 360, hence you see this kind of sawtooth pattern play out here. If we take a look at our semi-major axis, we can see that we're slowly starting to deorbit as well. So the drag on the satellite is pulling it down to a lower orbit, which is decreasing the orbital period. It's decreasing the semi-major axis, and it's increasing the mean motion. So we're getting more revolutions per day. You can see here that plays out in both the apogee and perigee, both decreasing. This orbital element history plot is very useful. If you are logged into the UDL, you can toggle on different sensor providers. I'm not going to show this here just because I want to keep this at unclass using public data. but it's useful sometimes to be able to compare and contrast different sensor providers' perceptions of the world as well to see if they're in agreement, or do they disagree, and by how much. So it's very useful to be able to toggle on different sensor providers here as a part of your analysis. So that's the orbital element history plot, really useful for determining previous patterns of life for spacecraft, which can inform our estimates of what a spacecraft is going to do in the future, if we know what its pattern of life has been like in the past. As I said, it's a bit of a lagging indicator, but it's good for long-term trending, particularly at Geo, where things play out over a bit longer time frame. So that's it for this video. Please like, comment, subscribe, leave any feedback in the comments, and I'll make sure I get back to you. And happy hunting.